Welcome to Calculus. Today, we are going to explore a powerful mathematical shortcut known as the Leibniz rule. If you have ever dreaded taking multiple derivatives of a complex product, this rule is about to become your absolute best friend. We will build your understanding from the ground up. So let us dive right in. Let us start by understanding what the Leibniz rule actually does. Imagine you need to find the 10th derivative of two functions multiplied together. Using the standard product rule over and over would create a massive, tangled mess of terms that is almost impossible to track. The Leibniz rule is a shortcut that lets you jump straight to the final answer in one clean line. Interestingly, it uses the exact same combinatorial logic as the binomial theorem from algebra, because at each step, you are essentially choosing which function gets differentiated. Now that we understand the concept, let us look at this connection visually. On the left side of the diagram, you see the familiar binomial expansion for a quantity cubed, giving us the coefficients 1, 3, 3, 1 from Pascal's triangle. On the right side, we have the third derivative of a product using the Leibniz rule. Notice how the coefficients are exactly the same? The number of ways to choose which function gets differentiated at each step perfectly mirrors how we choose items from a set in algebra. This visual connection leads us directly to the mathematical formula. The Leibniz rule uses a structured summation to organize all the terms generated by taking multiple derivatives. The symbol n represents the total number of derivatives we want to take. The binomial coefficient tells us exactly how many ways to distribute those derivatives. As the index r increases from 0 to n, we take fewer derivatives of the first function u and more derivatives of the second function v. This perfectly scales each term without missing any pieces along the way. Before we move on, let us see this formula in action with a concrete example. We want to find the nth derivative of x squared times e to the power of x. The trick here is choosing which function is u and which is v. We choose v to be x squared because it is a terminating function, meaning if we differentiate it enough times, it eventually becomes 0. We set u as e to the power of x since its derivative is always just itself, making our substitution incredibly straightforward. Now that we have our setup, let us find the sequential derivatives of our v function. The first derivative of x squared is 2x, the second is 2, and the third is exactly 0. Because every derivative after the second one is 0, all those later terms in our infinite series will completely vanish. This is the beauty of choosing a terminating function. We only need to write out the first 3 terms of the Leibniz expansion, saving us a massive amount of calculation time and effort. Let us finish this calculation to get our final result. We substitute our specific derivatives and the standard algebraic equivalents for the binomial coefficients into our truncated formula. Next, we simplify the expression by cancelling the 2 in the denominator with the 2 from our second derivative. Finally, we factor out the common e to the power of x term from every single piece. This gives us our final elegant equation. You can now instantly calculate any derivative of this product just by plugging in a number for n. Since we just derived a general formula, it is always good practice to verify it by testing a small known case. Let us check if our final answer actually works for the first derivative, where n equals 1. We plug the number 1 into our newly derived formula wherever we see an n. The constant term at the end contains 1 minus 1, which is 0, so that entire piece vanishes completely. This leaves us with a simple, clean expression for the first derivative, acting as a sanity check. To see if our shortcut worked, let us calculate the first derivative manually, using the basic product rule on the original function. The rule states that the derivative is the first function times the derivative of the second, plus the second times the derivative of the first. Factoring out the exponential term gives us the exact same expression we just found. They match perfectly in every single term, proving our shortcut is reliable, accurate, and ready to use for much higher derivatives without any hesitation. Now let us tackle a harder problem, when neither function ever differentiates to 0, like e to the power of x times sine of x. Because neither function terminates, we must keep the general summation form intact. We set u as sine of x. Every time you differentiate a sine wave, it shifts to the left by 90 degrees, or pi over 2 radians. We set v as the exponential function, which simply remains itself no matter how many times we differentiate it, making it very easy to work with. With our general derivatives found, we substitute them back into the full summation formula. We place the shifted sign function in the u position and the exponential function in the v position. Notice that the exponential term appears in every single piece of the sum and does not depend on the changing index r. Therefore, we can factor it completely out to the front. This provides our final elegant answer, representing the exact nth derivative as a beautiful series of shifted sine waves. Now that we have successfully used the formula, let us understand why it works by deriving it using mathematical induction. Think of mathematical induction like knocking over dominoes. First, we check the base case where n equals 1. This gives us the standard product rule, which we know is undeniably true. So the first domino has successfully fallen. Next, we assume the formula is true for some arbitrary positive integer m, and we write out the summation for that step. This sets up the foundation we need to prove that the rule must hold for the very next step in the sequence. To find the next sequential derivative, we must differentiate our assumed expression for m one more time with respect to x. We apply the standard product rule to each individual term inside the summation. This expands our equation into a longer series, where the derivative orders of u and v shift up by 1. By carefully shifting the index of the summation for the second half of the terms, we can align the pieces that have the exact same derivative orders. This step requires careful algebraic bookkeeping to ensure no terms are lost before we combine them in the next phase. When we group these aligned terms together, we end up adding adjacent binomial coefficients. This specific addition is a famous property called Pascal's identity, which states that adding two adjacent numbers in one row of Pascal's triangle gives the number directly below them in the next row. Substituting this identity back in yields the exact Leibnitz formula for m plus 1. Since assuming it works for m guarantees it works for the next step, all the dominoes fall. We already know it works for 1, so it works for 2, 3, and so on to infinity, completing our mathematical proof. So, we have proven that the rule holds. But why do we care about this in the real world? In physics, especially in quantum mechanics, scientists use this rule to take multiple derivatives of complex wave functions to find the energy states of a quantum harmonic oscillator. Without it, the algebra would be tedious and error-prone. It is also heavily used in electrical engineering and signal processing to analyze fading radio signals or dampening acoustic waves, helping engineers understand how these signals accelerate and change over time. Let us wrap up what we have learned today. The Leibniz rule is a powerful extension of the product rule that lets you find higher order derivatives instantly. By borrowing the logic of the binomial theorem, it completely bypasses tedious step-by-step differentiation. We saw how choosing a terminating function makes the math incredibly simple. You now have a systematic tool to conquer complex calculus problems.